problem. Okay, welcome everyone. Let's see here, share content.
Sure, at the end of the class, we have a couple of questions about the homework.
Sure. We're going to go over the homework. That's the purpose of the class.
Over both?
Yep.
Awesome.
Yep. So hopefully your questions will be answered. Your wildest dreams come true. All right, TCP header and IP header. All right, pull up homework 4 first because we can review that one. We're going to go over both of them. Enough people in the other sections had tons of questions on them that it's just not fair to just not do it, you know, for everybody. So we'll make sure you guys understand the concepts because they'll be on the test. I don't want anybody leaving here wondering, you know, do I really understand this or not? So the goal today is to make sure you feel like you're within reach of killing it, mastering it, maybe a little more study. Okay, so the first question had to do with addresses. And almost all the answers for this first problem are on either the TCP header or the IP header, with the exception of the 48-bit address. So what bits have we seen that are 48 bits? What addresses have we seen that are 48 bits long? Yeah, it's the only one, Ethernet. And a layer up from that? The layer up from the layer 2 MAC address, it's 48 bits?
There's 48 bits.
No. It's a question. What's the layer above data link? And what's the addressing scheme there? IPv4, and how many bits are in that? 32. Do you see the pattern yet? And the next layer up? Transport layer? 16-bit port numbers.
Oh, it's port number.
Well, that's one possible answer. I don't care which one you pick. There are more.
I think assembly addressing.
Okay, well that's kind of where I was headed. Is like layer 2, layer 3, layer 4. Right? Make sense?
Yeah.
Okay, and then addresses. We've seen 4, 8, 13, 16, and 32-bit counters. And skipping past addresses for a minute, things that count how long something is, or tell you how long it is, or are counters. So, you know any 4-bit counters? Yeah, the header length. So if we go over and look at this, this is a 4-bit value. It tells you how big the header length, how big the header is. So that one's the smallest one that we've got, and then there's an 8-bit one. So if we look for an 8-bit counter, TTL is one of them. Yep. So time to live is an 8-bit counter. No, it's not linked. It's just a counter. It could be either one. And then 13-bit, there's only one in the world. It's the fragment offset, the bane of my existence. Well, and then it's super hard for everybody to understand. And I still haven't found the magic 10-second way where people go, got it. You know, it's like, I have to like go through it, and I'm like, there's got to be a better way to explain this. So anyway, everybody's kind of at a different point, but 13 bits, that one's hard for people. 16-bit, you've got choices, but checksum, I don't know if it's a counter. It is a counter because you're adding everything up. So I would count that as correct, I think. But are there other ones? Okay, and also receive window size. Right, when they're telling you how much space they have left in red over here to receive more data, that's a counter as well. Also, the IP identification number is a counter. It's a serial number that the IP layer gives to every datagram that leaves. Yeah. It's not a separate counter for each TCP string or for each socket or for each program. It's just one for the whole thing. Every time an IP datagram cranks out, it gives it a serial number. It's a unique ID for each. Yep. And when you fragment a packet and you split it up into pieces, all the pieces keep that same one number. That way you know to put them together again. Yep. When they run out of the system, like in a day? It will restart. It'll roll over. All these things will, all the ones that are counters will roll. You know what I'm trying to say. I can't even say it in English. What hope do I have of saying it in Spanish? It's never going to happen. Yes?
What did you say was the 13 bit?
Take a pic here in the packet. It's right here in blue. It's this fragment offset. Do you guys remember what that is?
give us your 10 seconds. Yes, yes. I
Yeah.
remember what
Now don't smirk and sneer at me. Don't taunt me.
I remember what the fragment was.
Yes, tell me.
It's an identifier for when a IP packet needs to be fragmented into different fragments. Yeah. And it tells us like in which bits start each of the.
Yeah. So here's the problem. You can have a let me get the right kind of pointer here. You can have a 16-bit datagram,
Yeah.
and it can be too big for the network. Most of the time when we think about fragmenting, we're thinking about breaking something up into lots of little pieces. So those are supposed to be lines, like 20, 30 packets, but not necessarily. You can have a maximum size that your network can handle that is almost exactly the entire length that you would be allowed. All right, so that's the problem. And so if I can turn this off, where did my little thing go? It hit on, it just went away on me. Okay, where's my little editor here? Barra de herramientas. It's just gone. Really?
Which?
The one that has the place to turn the freaking box on and off.
Oh, I don't know.
It's like it was up at the top. It has a bug. It goes away once in a while. I'm just gonna have to quit and start it again. It just does that. Drives me crazy, but hey, it's a whole lot better than WebEx's drawing tool, so I'm not gonna complain. All right, so the idea of this offset is to tell you how big something is. Now, why do you need more than 13 bits to tell you something? Isn't it usually the case that when you're busy dividing up a packet, don't you always divide it up into lots and lots of small pieces? Well, no, not necessarily. It doesn't have to, look like this. If this entire packet is 2 to the 16th in size, then you don't need very many bits at all. I don't know, maybe like 2 to the 10th or something like that to tell you how long this thing is, and then another 2 to the 10th. So why am I complaining about not having all 16 bits? And the reason is because you can have a network that could handle almost all of the entire packet, except maybe the last 50 bytes. It's possible, right? So you could have one. In that case, the length of this segment here, excluding this last piece, would be 2 to the 16th minus 50. So how many bits do you need to represent that number? Well, 15 at least, close to 16 bits. So that's why I'm complaining. So how are we going to get around it? So if I told you you had 2 to the 16th bits, and I took 2 of them away from you, you would have 14 bits left, correct? If I told you I was going to take 3 bits away from you, you'd have 13 bits left. Well, what's true about math here is that I can multiply both of these sides by 2 to the 3rd, and these cancel out, and now I'm left with, obviously, 2 to the 16th equals 2 to the 13th times 2 to the 3rd. So if you only have 13 bits, each one of them has to represent 2 to the 3rd size. It's just that simple. So every number, when I count up 13 bits, when I count up 0, that means it's 0 bytes. When I put 13 numbers down and the last one's a 1, it's 8 bytes in length. If I put down 2, it's 16 bytes in length. So as long as you're willing to write the code to pad every single fragment to a multiple of 8 bytes, this scheme will work. And you don't have to have 16 bits. You can just get away with 13 bits. Right? How'd I do? It's a totally different way than I've ever described it to you guys before. I did the math thing this time.
The math thing last time.
Well, not quite like this.
That's not the same math. I left the room because it was, I calculated that always, but I already knew.
Yeah.
But then you started no, that's
It's different than what, yeah. So the relationship is with when you have less bits than you want, you have to make up for it by making that smaller number count multiples of bytes, not just one at a time. If you count them one at a time, you're going to run out at 2 to the 13th. And I just showed you an example of where you need more than that. So just make them multiples. We see exactly the same thing in the IP header. I would have really liked to have had like 6 bits or something, but I only got 4. So just make each one of those counters a multiple of a few bytes apiece. This happens all the time in protocol design. In fact, I would imagine that since fragmentation was not originally part of the design, I mean, who would have come up with that crazy scheme? I could imagine a scenario where the guys that wrote this said, okay, we have 2 bytes that we can take out of commission that are left in the header. Can you get what you need done in 2 bytes? Because that's all we have. Well, then sure, I can do it. All right, here are your 2 bytes. I'm going to kill off what was there. We're going to move those 2 bytes, and now they're for fragments. So they go back and they go, crap, what are we going to do with 2 bytes? I have to have these 3 bits. You've got to give me those 3. Well, then you only have 13 bits left. Well, then what are we going to do? And they figured out, well, let's just make them multiples of 8. Right? Always. For that particular one, it's always going to be the number of bits you had, the number of bits you're now given, and how many you have to make to get back there. This is the multiple, always 2 to the 3rd. If I told you you had a 20-bit number, and I'm going to rob 5 bits from you, so you're only going to have 15 left, every one of them is going to be 2 to the 5th in size. So if you do that, if you're good about doing it, then when you get to the maximum number you have here, because you're multiplying it by this, you get back to the same value that you had before. Yeah, okay. Yeah. Yeah. Okay. Okay. Gringo nails the fragmentation thing. All right, good. So that's number 2. Number 3, consider the following IP addresses. So this is one just to see if you guys are comfortable doing and, ors, and nots. And that's it. So we can do this one easily. Okay, I can show you. You'll see it. All right, so this is, let's make up an IP address. I don't think it's really 32 bits. And then here's my subnet mask. Okay, so for a router to figure out if it has an entry in its routing table, when it gets an IP datagram in the door, the first thing it has to do is strip off the subnet mask, if it can figure that out. So if I give you the IP address and I give you the subnet mask, what do you do to strip off all of the host bits? Because what you really want for a network number is you want a 32-bit IP address where these are the same and all of these are zeroed out. So just AND them. You AND them together, and that's exactly what you'll get. Right? That's B. The number of IP addresses available, did I tell you how many? It was a 19? Yeah. So if you have a /19 network, that's how many bits are reserved for this part here. 19 bits. How many are left? 32 minus 19, right? And then how many addresses can you make out of that number of bits? 2 to the that. It's that simple.
So we will have to use the NOT?
Well, not for the A. A is just asking you a numeric question just to make sure you got your arms around it. Yeah. You could do a NOT and look at that number. And that number is how many you've got. But really what you should do is look at the NOT and add 1, because that's really the number in decimal of addresses. So you see what I'm saying? So how many addresses do I have here available? One way to do it, it's an alternate way, is make all these zeros, make all these ones. This is a binary number, right? It represents some number. Add 1 to it, and what you're going to get is this. Figure out what this is in decimal, and that will be your answer. How many addresses you've got.
Will we have to subtract the gateway?
No, don't do that. No, because that's been just a huge pissing match for years. There's no reason in the world why you cannot assign the network number to a device. After all, is somebody else going to use it for something? Is anyone going to come up and go, I'd like to send a packet to the network, please? What are you going to say? Well, like, do you mean like a broadcast? Or like, nobody will even know what that means. So let's leave the broadcast alone. I mean, that one I agree. But the network number, every router manufacturer gives you the ability to use that address as well. They all do, and have for decades. So I don't like to get into the fight. Is it like 2 to the n, or is it 2 to the n minus 1, or 2 to the n minus 2, or if you're left-handed, it's 2 to the n minus 3. And so just order of magnitude, 2 to the n is good enough. If you subtract 1 or 2 from it, don't go back and change it. I'll count it as right. I don't care. It's not important. And if we're getting really detailed, then yeah, but we're asking concepts here. Yes, sir.
In that one, I
Yep.
think, well, I have the not n plus 1, but I have it divided by 2. Because if you have, say, 19 ones,
Let's do a 30. Can I follow along with you?
okay, yeah.
All right.
You have 30, right?
So I have all these zeros.
And then the last 2 bits are 1.
Yeah. When I knot the subnet mask, that's what a /30's inverted subnet mask looks like, right?
Yeah.
So if I add 1 to this, what am I going to get?
0, 0, 1.
1, 0, 0, right? Which is 4. How many addresses are in a /30? Yeah.
Yeah.
I think it is +1. Now, divide by 2, you could talk me into something, right? Yeah, very, very similar. You guys learn 2's complement? Okay, yeah, of course. Yeah.
Like only like.
How to do addition, how to do subtraction with only addition?
Yeah.
And did you learn how to do multiplication with only addition?
Yeah.
And division with only addition?
Yeah.
That drives my students insane.
It drives me insane.
Because we have this number, right?
Yeah.
It's,
No vayas a reír en la pantalla.
no.
Yeah, I did that once. Don't do that. There's already a Kevin Long memorial screen out there. We don't need 2 on campus. I don't want to buy another
Oh,
one.
no. We took from 0, right?
Yeah.
Yeah.
Okay, then no.
Yeah, okay. Yep. I got you. If you count from 1, you're going to have to do that.
Yeah.
Right? So it's good to always be careful. You know, that's an easy problem. The problems that we make in the U.S. are things like we build a Mars lander for $200 million and we send it there, and the crew that's supposed to land it did it in miles, and the crew that did, so we crash the thing, we just impale it into the ground 1,000 feet down because we thought we had 100 miles to go instead of 100 kilometers to go. I mean, how stupid, how embarrassing.
Yeah. Yeah.
How can you not go kill yourself after you do something that stupid? Like,
The other story that makes me like laugh really hard, and I understand now, like why would you do that? It's the thing with the pen.
he's back again.
Yeah, no, I
He can't let it go.
No, wait.
He's like that sometimes. He's like that.
That's why you guys are here. That's why you're at Tech.
If you have 0,
Need one. Yeah. Come on, then.
yeah, no.
So the /30 goes up to and including the 30th bit. Doesn't stop at 29. So if you count from the left 30 bits from 0, you will stop at 29, and you'll have 3 bits left, and you will have to divide it by 2. But we count slashes. You can't have a /0. There is no such thing. You have a /1 and all the way up to a /31. That's it. So you count over 30 bits, and you have 2 left. Them are 31 and 32. And that's why it's 2 squared, and you're okay, +1. You know, to set both 1 and, okay, so number B, if you want the network number, we already did that, and the 2 things together. Okay, what about the network broadcast address? What is the network broadcast address? It is, and so tell me what that looks like. If this is my network number and this is one of my IPs out of the group, how do I turn this into a broadcast for only that network? It's exactly what you just said. So tell me what I changed that to. Yeah, you don't change the network bits because it's not a broadcast for everybody. It's just a broadcast for everybody in this subnet. So you change all of these to 1s. It's exactly the definition you gave, the last IP address in that subnet. Okay, so how can I create that given this and this, only the things in blue? So flip the subnet mask, right? So I have that now, and then do what?
And then with
OR it, so a NOT and an OR. So if I OR this with this, I'm going to get 10110100111 because that's this or that, and all of these will be 1s. These are exactly what the routers will do to figure these things out. They don't have time to do any other kind of math. So the CPU on the system will take a few milliseconds to calculate an answer like this. You have a few picoseconds, typically, maybe if you're lucky, nanoseconds to do it. So there's no way to do this except in hardware. Okay, So the next one is a question about base 256 math, and you will see one of these on the test. So there's two ways to, yes,
In that one,
yeah,
we assume we need to take one from the
no.
other.
And I tried to word it carefully. Don't go back and redo it if you did. I won't count it wrong. But I tried to be careful to say the first address has already been assigned. You're told now there are this many additional addresses in the sequence.
We're already taking from that double partition.
Yes, yep. So you don't have to subtract one at the end. So what he's talking about is if I start with an address that ends in this and I give you 8 addresses, the last one is not 8. It's 7. Right? So you have to subtract it. But you don't have to worry about that in this one. Okay, so there's two ways to do this problem. You can take your IP address and you can convert it to a decimal number. And if you had to do that, you would do 10 times 256 to the third plus 49 times 256 squared, because remember the day we did positional numbering systems? 168 times 256 to the 1 plus 252 times 256 to the 0. And you will get a decimal number out of it, and you add this 50 million to it, you get your new number, and you go backwards. Just reverse what you just did again. That's one way to do it. The other way to do it is to start with 10.49.168.252 and convert the 50,595,078 to an IP address. So let's do that way. Does that sound okay? So in positional numbering systems, what we learned, if you remember, is we start with the biggest number possible and we see if we have enough to fit in there. If we do, we mark it down, we subtract it, and the remainder is what moves to the right. So we are always dealing with the remainder. If you have $1,000 and 1 cent in your pocket, the 1 cent is the remainder. You had $1,000 and what's left over? The 1 cent. So we're going to move left to right. So I have my 50 million, and I'm going to need you guys to help me do the math with your calculators here, okay? And it's a good time to practice this on your calculator. If it can't do 256 cubed, this window opens.
Throw it away.
Yeah, do you guys know what a sail cat is?
Sail cat.
Sail cat?
No.
It's a cat that's been run over by a car, and it's flat like a frisbee, and you can sail it.
Like el gato volador.
Yeah, well, yeah. I'm about to tell you the story of sail cats. So it was also, they also made it into a cartoon once, which I totally flipped out. I could not believe it. Oh, my God. All right, so how many times will 256 cubed fit into this number? So I'll do this first one, but you guys got to help me do the rest. 50,595,078 divided by 256 cubed. It'll fit 3 times, but not 4. I don't know whether to say salute or not, because it wasn't really a full-blown sneeze. Do I just say sa? Sa? Okay. Okay, salute. All right, so it'll fit 3 times, but not 4. So my first number, when I convert this, is 3. So now I've got to subtract this from here. So I'm going to do a little math trick here. Now I want to subtract off 3 of these things, so minus 3 times that. And this is my remainder, 263, 430. 263, 430. So the remainder is 263, 430. After I take 3 of these off here, I'm left with this. So it really shrunk it. I have very little left. All right, so now I'm down to the next position. I want to know how many times will 263, 430 cover 256 squared. It'll fit 4 times, but not 5. So I just divide it by 256 squared. So my next number is 4. And what is that? I'm just going to subtract off 4 of those now. And that gives me my remainder. So 3 times 256 to the third plus 4 times 256 squared leaves me with 1286 to account for. I'm almost finished. So 1286 is the next number. And what I want to do is see how many times. I'm not going to take any shortcuts. I'm going to do the power to the 1 and the 0, the whole bit. So now I'm going to see how many times 256 to the 1 will fit in there. And it fits, sorry, I got to put the right remainder in. Thank you. What's really frustrating is I did exactly the same thing in the other 2 sections. Only on the third one, just like this. A creature of habit. So it'll fit 5 times, but not 6. So my third tuple is 5. And what does that leave me if I subtract 5 of those things? It leaves me with 6. So my IP address is 3.4.5.6. Clever, huh? You want to guess what I gave last year's class?
1, 2, 3, 4.
Yeah. Guess what you're going to get on the exam? It's a short list. 2, 3, 4, 5, 4, 5, 6, 7, 5, 6, 7, 8. Yeah. So if you do one of them, if I were you, I would just check the next, just try it and just see if the first one is like 4, go 4 times 256 cubed plus 5 times 256 squared times, and just see if it adds up, and then you're like, yeah. It's more fun to do it, but it's also fun, isn't it, to like guess, like, I know what you're doing. I see what you're doing there. I see what you're doing there, okay? I got you. All right, so now we got to add these things together. So we can start from the right or we can start from the left. That part I don't really care. There is a right way to do it, but let's just have some fun. 13.50 what? Right, and then 168 becomes what?
124.
And then 252 becomes what? 258. So are we done? What's wrong?
You need to carry.
I need to carry. Why do I need to carry? This is a base 256 number. In IP addresses, every one of these numbers has to be between 0 and, it has to be between 0 and what? 250 what?
The 174 was a 173. So
Thank you.
you.
Oh, thank you. Yeah. Okay. So because I'm in base 256, every number has to be between 0 and what? 255. If you get confused and you think it's 256, just remember in binary, base 2, your valid numbers are 0 and 1. In base 10, 0 through 9. You always take one off. So in base 256, your valid numbers here, 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 and here, they have to be between 0 and 255. And that makes sense because we only have 8 bits anyway, and that's the biggest number you can put in 8 bits, which is why they did this. So this one's a problem right here. It's too big. So I'm going to subtract 256 from it, and I'm going to get 2, and I add 1 over here, because I really could have fit one more of those groups of 256 times to the power of 1 in here. All right, you think you can do this, or you want to do another one? Some of you look very lost. ¿Quieres hacer una otra o todo bien? Okay? Okay, bueno. All right, the sooner we finish, the sooner we finish. Okay, what I'm asking you here is, what's going to come up now are 3 or 4 different ways of going after the same problem. I want you guys to get used to coming after these subnetting problems from a variety of directions, so you have some skills around doing it. So I have a 32-bit address. The first bits are my network number, and the remaining bits are host bits. And if I ever design an alphabet, I'm not going to make N and H look almost alike. You're welcome. So I'm given the N bits, and that's a rule. It means all of my IP addresses must start with these N bits. I can never change them. I could do whatever I want to the rest. So let's say they give me this big block of H, and it's 2 to the H addresses that I've got, and that's just too big of a block. I don't want to do that. I want to break it up into pieces. So the first thing you got to remember when you do the breaking up, you rob bits from here. You do not rob them from here. Salud. So if I need something in the number of groups, if you can tell me how many groups you want, then I can put it into this equation. Let's say you tell me you want 2 groups, then I need 1 bit to do that. But you guys already know that. So I'm just showing you the equation for it. So I'm going to steal 1 bit, so this becomes H minus 1, and now I have 1 bit here, and that means that out of all these addresses, the H minus 1 addresses run from 0s to all 1s. Correct? Half of them will have as the N plus 1 bit a 0, and the other half will have 1. So you'll have 0s, and then another group will have the same pattern. And presto, you have 2 groups, equal size. The first group starts with a 0 on this bit, the next group starts with a 1. If that is not correct, may God fix that light. All right, there we go. So if you need 2 subnets, you only need 1 bit to keep track of 2 things. So that answer is 1 bit for part A. Okay, for 100 subnets, how am I going to figure out how many bits I need? I would use this equation. Yeah, it'll be 6 point something, but I don't know how to cut out 6 point something bits. So I'm just going to cut out 7 bits. I need more than 6, obviously, so let's just make it 7. So if this becomes 7 bits, then I have h minus 7 bits left. So out of each of my 2 to the 7th groups, the first one is going to have these 7 bits, and the last one's going to have these 7 bits. But that's not all. I have my n bits up front. I have my subnet bits now that I've just figured out is 7. And then I have the rest of the bits are host, which is h minus 7. So that's still a lot of addresses. It's a ton of addresses. But that's how you're going to do it. If I need 256 subnets, you could run through it again, but I would just say that you use 7 this time. If you double this number, you're close to this, so why not add 1 more bit? That's another way to do it. You add 1 more bit, you double. 1,000 is 4 times this one, so why don't you just add 2 more bits, multiply it by 2 twice. My guess is that this one is 10 bits, so let's go see if we're right. Log base 2 of 256 is 8, and log base 2 of 1,000 is 9.9610. So you can sometimes save yourself some time, or at least look at it and figure out, does this make sense? So just remember, when you have a 32-bit address and somebody tells you how many of those bits are for the network number, you have 32 minus n left. And let's assign that to a variable like h. But it's really 32 minus n. And if you start robbing more bits for subnets, then you just start taking off more and more bits. S bits here. So it's got to all add up. So let's do it from the opposite direction. All right, so I start with 32 bits. And my question is, let's see. You're given a network. You need to allocate subnets. You notice that you can allocate at least 1. What is the equation for how many of these subnets you can actually allocate? Okay, the reason I'm doing this is because usually if you go into a customer, they're not going to tell you, I need 16 subnets. They're usually going to tell you, I got 100 devices over here, I got 300 employees there, I got 64 things over here, you tell me what I need. If you walk into a customer and they tell you exactly how many subnets they need, then just say, great, we're done, see ya, right? And you can walk out the door. Because they obviously know what they're doing, or they're going to be so arrogant you're never going to get your job done. One of the two. Here's another thing to remember in your career. I have never once in my life seen a network manager who has an accurate network map. They don't exist. I've convinced myself it's an impossibility. If somebody ever creates one, I'm convinced the world will end. So an accurate network map. No one has an accurate network map. Maybe it's relative. They don't have something. They don't have a map that shows that how every address is assigned, to what device it's assigned, every subnet. They never have an up-to-the-minute view of it. So if it happens, I think the world will probably end. So don't try too hard. But it also means something more important. It must not be that important. Because networks work without them. So, you know, don't sweat it trying to build the perfect network map. You can't. I had one customer that thought he had it once, and so did I, and then we realized, oh, God. So, all right, so what I'm asking you is if you walk into a customer, a real customer, and they tell you, I need 100 addresses here, I need 400 here, I need, you know, whatever, and they tell you how many addresses they need in each subnet, then how do we calculate how many of them they can have? So I start off with 32 bits. I know that my network bits are not available to me, and they tell me how many addresses they need in each of these groups. So how do I figure out how many bits that is? We just did it like 3-4 times. If you tell me, Mike, you need 1,000 addresses in your subnet, How do I figure out how many bits? You take a log, yep, you take a log base 2 of whatever that number is. Now, I didn't really give you the number. I gave you a variable. So it's log base 2 of m. That will give you the number of bits here. How many are left?
N minus log base 2 of m.
32 total bits, right? Minus n for your network bits, minus log base 2 of m. Now you have to worry if this needs more bits than are left, but all this other garbage in here tells you that's not going to happen. Those are your safeguards. So how many groups, how many different subnets can you build then? That's not quite it. This is a number between 0 and 32. What do I need to do to this? This will tell me how many bits. Yeah, 2 to the power of that. That's how many subnets I can have. 32 minus n minus log base 2 of m. That will tell you how many bits are here. Yep. Make sense? I told you the slash n, so you've already got this number of bits. That's exactly what this is, this number of bits. So you started with 32 bits that you could play around with. I've already taken n of them away. So it leaves you with 32 minus n. And then I made it a little harder on you. I didn't tell you how many bits I needed. I told you what a real customer will tell you, how many IP addresses I think I need in a subnet. So if they will tell you that number, m, you can take log base 2 of that number. And for this exercise, I told you it was always going to be a power of 2, just to make it a little faster. So that's going to tell you how many bits are here, so that you don't have those to play with either. What you're left with is the number of bits here. And so let's say we do the math on a real number and it's 5. Let's say it's 5. How many subnets can you build with 5 bits? 2 to the 5. Salud.
Okay. So that's like the amount of combination.
Exactly. Exactly. And then I gave you part of a table to sort of figure this out. So we can do a real one. So suppose I have 32 bits, and I tell you my network is a /15. So I'm in this row. So I'm going to subtract 15 bits off. And then how many do you want each one of these networks to have? 32, 64, 256 addresses? 64? All right. So I'm going to take, if this works, I should be able to take log base 2 of 64 and raise this whole thing 2 to the power of that. So what does this give me? 2 to the 32 minus 15 minus 6. So equals 32 minus 21 equals 10. Is that right? 11? All right, so what's 2 to the 11th? 2048. 2048. So let's go back and look. Here's my row 15. Here's my column 64, 2048. So if you're not sure you have the right equation, you can use this and just double check. All right, make sense? Okay. Keep going? All right. ISP design. This one requires remembering what we talked about with carriers. So if you are an ISP, you can probably count on the fact that your customers don't want your other customers to see their traffic. Correct? Just like you don't want them to listen to your phone call either. So the phone industry has been built around this concept of private lines. Everybody gets their own circuit that goes all the way back to the trusted building. From there, they can do what they want, but nobody can touch it inside the building. So as long as it's a dedicated pair of copper wires that only you are on, then that's considered secure. So that's the way the whole world's telecommunications network was built. And they just keep that rule when they build any other kind of service. So let's say I have 100,000 subscribers. So they're all going to come into a router. So I'm going to have 100,000 router ports. I'll do it logically. I won't do it physically, but logically there are 100,000 router ports. So what do you have at the end of each one of these cables? What do you have at your house? What did the Telmex guy in the white truck drop off? A router, right? All right, and you have a LAN with some devices at home, probably Wi-Fi, and a printer, a laptop, a tablet, a couple of phones, stuff like that, right? Okay, so there's one LAN here. I want to change the size of this. Hold on. Is there another LAN on here as well? Mm-hmm. Every router port is on a LAN. I see 2 ports on my router, one on my side, one on their side. So where does that LAN go and where does it end? Just to this router port right here. You have your own, or else it would be shared. And you already said you didn't want it to be shared. So I have 100,000 subnets. Pull up your network. You probably have, yeah, just look at the network mask. You probably have 192.168/16. You may have a 172 number. I have seen that in Monterey before. But if I go to my settings and, whoops, look here. Here's my subnet mask. So what is 240 in binary? Yeah. Is it at least 128? Is it at least 192? And if I add 32 more to that, so what's it gonna? So subtract 15 from 256. So it's going to be 1 except the last 4. So it's that 1 1 1 1 0 0 0 0. That's 240 in binary. So you have a /20. 8 bits for the first one, all ones. 8 bits for the second one, all ones. And the first 4 bits are ones. 8 plus 8 plus 4. You have a /20. So how many addresses do you have? 2 to the 32 minus 20. 2 to the 12. 4,096 addresses. Here at Tech on this LAN. So there's 4,000. Now it's my turn. I'm catching up. So just look at your subnet mask. You will probably have a /24. Okay, so back to Telmex, back to our carrier. So now I see that I have this router with the LAN off the end, and I'm just going to put me, this is Telmex, and this is me. And I have a connection here, and we've determined that I only have 2 devices on this LAN, right? So tell me how many addresses I am going to need to build a LAN that has 2 assignable addresses. Remember what you were asking earlier? Do I have to subtract 2, and you remember? So you have to have a broadcast address, and you need 1 address for here, and you need 1 for here. But you can only have networks with powers of 2 numbers. So it's got to be 4, right? You only are going to use 3, but you can't build a subnet with 3. You're going to build a subnet with 4 addresses. 1 for this end, 1 for this one, 1 for the broadcast address, which they're probably never going to use. I mean, after all, just send it to the other guy. There's only 1 of them. And the network number, which we don't care about. So we're going to have 4 addresses, public IP addresses, for every one of these networks. So
For purposes, can you just make like an address with a broadcast and then the receiver that has the same address?
Probably there's better schemes to manage this, and there's probably some in use that I've never seen. But every time I've ever seen carriers do this, they always use 4. So what's my subnet mask? So I need 4 addresses. So log base 2 of 4 equals 2. So I need 2 bits for my devices. I will get 00011011. This is my broadcast address. This will be one router, this will be the other one, and this one I'll just ignore. So if I'm using 2 bits for that, the other 30 are available. That's my network number. So carriers have a ton of /30 networks. They will need 400,000 addresses, not 100,000 addresses, to get 100,000 customers up and running. It's quite incredible that we have enough addresses to do this, because there are millions and millions of people that have these /30s. Many hundreds of millions maybe. So it's a miracle. All right, so your subnet mask for each of these will be a /30. That's what you guys are telling me. How many total addresses will the ISP need? For 100,000 users, how many is he going to need? 4 times as many, right? 400,000. Refer to the spreadsheet and the homework folder on the drive that says prices. So let's go shopping. Want to?
Is there a way to find what I do to refer? So, the connection with the ISP?
Yeah, usually the carriers now will let you log into the router. So if you have a Telmex device, just try logging into 182 or 128, .1.250. I can't remember the number now. And then the serial number is the WPA Wi-Fi password on all of the Telmex boxes. I've already hacked the hell out of mine, right? So it took like 5 minutes. But you log in to it, and then it will show you what it's using on the WAN side. So this reminds me of a very important joke that he's going to miss. So, yeah, no, it's okay. So I thought this story was real for many years, and then as you get older, you realize it can't be. It's an urban legend, but it's still a very funny joke. So the story was there was a professor at my university in physics who never gave a practical problem on an exam. They were just purely theoretical. And so people complained about it, and he decided he would give a practical question. And so the question was, there's a new skyscraper built in Houston, Williams Tower, and you have a barometer. Tell me how to calculate the height of the building. And what he was looking for was the equation for barometric pressure. You would measure the air pressure at the bottom of the building and the air pressure at the top, and you would show the equation, and you could deduce how tall the building is. And I suppose a few people answered that way. But what made this famous, and probably fake, are the list of answers that he got. One of them was, go up to the top of the building, throw the barometer off the side, and using the terminal velocity equation and how many seconds it took to hit at the bottom, that totally works, deduce the height of the building. Another person said, go to the top of the building, lower it down on a string, and start sweeping out a pendulum, and just pick a degree, 10 degrees, 20 degrees, and count how long it takes to ascribe that thing, and then you can calculate how long the diameter is by how long it takes in 1g gravity to do that. Right? That will also work. That's a lot harder than barometric pressure, by the way. Then he had a few fun ones. Oh, there's another scientific one. Wait for a sunny day, measure the length of the shadow that the barometer casts, measure the length of the shadow that the building casts, measure the barometer, and using similar triangles, deduce the height of the building. Yeah. And then there was one that said, put on a Spider-Man outfit and climb the building, marking it off in barometers. You can deduce the height of the building for that. But the one that made me know that I was going to be in technical sales was the one that said, knock on the building superintendent's door and offer him a nice new barometer if he'll tell you how tall the building is. So it's like, that's the one I relate to, so I'm doomed. That's my career, obviously. There's no point in going beyond that. So you guys can now steal that and begin spreading it here at Tech.
I would make a shadow. Kevin Long is the one that's asking all the questions.
Yeah, you can make it me. I asked a question on the exam, and then you guys messed it up. Isn't that the funniest joke you've ever heard, though?
Oh, yeah.
Yeah, good. Huh? Oh, I'm sorry. There he is. All right, so let's get back to counting. Yeah, I'll tell you later if you want, or they can. And it'll be.
No, you told us the joke.
No, I didn't tell this joke.
No.
No. Tell him in Spanish so I can learn some of the new words.
No, okay, no barometer, but the older he is.
Yeah. Which one? Oh, yeah, okay, that's true. All right, so let's buy IP addresses. How do we know how many to buy? 400,000, you could buy a /10, and it's going to cost you $500,000 to do that. But you can buy a /10, and you would have enough addresses. You'd have tons and tons of /30s in there. That would be enough. So let's write that down. /10 will cost you $425,000. Yeah, it seems like a lot, doesn't it?
Yeah.
So what if you, instead of doing that, if you bought a pair of /11s? Well, you definitely don't want to do that because they're actually more expensive per address than the /10s, just because they don't know what they're doing. These are Lacnix prices, by the way. You could then go down, maybe try dropping a lower price. What if you bought /13s? They're less per address. How many /13s would you need? If you need a /10,
How many of those do
well, I want you to tell me with an equation to do it.
You would need to divide the
2 to the 13th times 2 to the minus 3 will give you 2 to the 10th. So you're going to be doing 2 to the 3rd. You need 8 of them. You're going to need 8 of them to get that done. So if I buy 8 of those, let's say I buy a /13, I'm going to pay 8 times $40,000, which is how much? You've just saved your boss $100,000. Think he's going to be happy? Yeah. Should we continue on down, or is there anything unusual that anybody sees? What do you see in the graph? What's the lowest price per IP? Let's go buy those. You want to do that?
Yeah.
So if I buy /19s, it's going to take times 2 to the minus 6. We'll get you back to 2 to the 10th. So I'm going to have to buy 2 to the 6 of these things. Oh, thank you. Yeah. Darn it, it's going to be a higher, bigger number now. That's going to be 512. So I'm going to have to buy 512 of these things. So what's that going to cost me? 512 times, he whips out his calculator, my peripheral vision, times $260, and he tells me the answer is 133,000. It's $300,000 less for exactly the same thing. Now, if you can get them to give these to you all contiguously, you can still advertise a /10 to the outside world. Just group them all together. And you tell them, do not give them to me as separate subnets. Let's group. They will be happy to do that, provided that they're not trying to use this as a penalty for buying small ones. They could force you to throw all of those broadcasts and network numbers away, pull out 1,024 addresses, but I have tons left still. That's okay. If they want to be jerks about it, then make them publish all those routes. That's all right. That's their feeling.
Because we divided the 13. We divided the number of
the total number of
192 over.
You divide it up into bigger clumps?
Yeah, so each server has 8,990.
Yeah, that's a better way a faster way to do it. It's more foolproof than this crazy formula stuff I'm showing.
But it gives a different result.
Yeah.
Well, yeah.
And all the way to the left, it says that it has 8,192, I believe.
Yeah, but I don't think it.
Oh, it's 100,000. We did it with 100,000.
No, we did it for 100,000.
So 2 to the, where is it? 2 to the 19th, 2 to the 32 minus 19 is 8192. It's correct. Shouldn't give you a different answer.
Yeah, but if you divide for 100,000 between 800,
it gives you 48 of these things. Oh yeah, why did I don't want to do 512 of these things. That's crazy. Why did I do that?
49. You need to
Yeah.
Yeah, you need 49.
49 times how much a piece?
60, which is 12,000.
Yeah, which is stupid, crazy, impossible, cheap.
Yeah.
So will that give you enough addresses? It should, right? It should. So I screwed up in there somewhere on the. I don't want to take time now to figure out why that doesn't work. I thought it would have worked, but the way you did it is the way I did it in the spreadsheet. I just divided 400,000 by 8,192 apiece, and took what was left. Okay. So what you want to aim at is this low point. I will grade this one by taking a quick glance at it. That's it. So I don't really care what answer you got on this, as long as you showed me you knew that it was more than 100,000 addresses, and you went and bought a block from LACNIC. If you want to go buy one block, you can. That's okay. And in fact, they may force you to do it if you try to buy them all contiguously. I'm like, yeah, I see what you're doing there. So they may want to encourage small businesses. So they may have a grant from the federal government of Mexico, or they may have a grant from IENA that says we will not charge you nearly as much for all of the /19s that you give out, because we feel like there's a bunch of those businesses that are underrepresented, you know, for whatever reason. Like there's somebody not on the internet. Give me a break. But it could be like that. Okay, you'll come up with answers to that. Now the subnetting one is one that's a little more style. So this gets into a little more ego, because, you know, who doesn't want a license plate that ends in all zeros, like 3 or 4 zeros? That's kind of cool, right? Who doesn't want a phone number that's super easy to remember? So, you know, there's ads around town where there's people that have phone numbers 888888888, you know. So they bribe their way for those. You have to bribe people in the U.S. to get those. So what I'm going to talk to you about is a little bit about designing a network, but doing it in a way where at the end it looks kind of cool. All right, so first thing I do is I'm going to glance through here and I see I need about 250, 350, 4, 550, 600, 700, 800, you know, about 1,000 addresses max, maybe 800 or 900 addresses, nothing more than that, right? So how can I get 1,000 addresses? Log base 2 of 1,000 is 10 if you round up. So why don't I start with a network mask of 22? You see how I got that far? I just am ballparking it. I don't know if this is going to work yet or not, but I added this up. They need, you know, somewhere around 1,000 addresses. So I'm going to give them a /22. All right, so what can I do with this /22? I could divide it up into, you know, 2 halves, but I have 4 groups. I don't have 2 groups. That's not going to help me much. So I need to divide it into something smaller than that. So how many does this have? This has 256 addresses. So that's enough for today, but not enough for 2 years from now. So they're going to merge. So somewhere along the way, 2 things are going to happen. They're going to cross the 256 boundary. They're going to show up and need their 257th address, and I'm not going to be able to give it to them with this. And the other thing that's going to happen somewhere in the next 2 years is Group B is going to merge with them. And I don't know which one's going to happen first. So let's plan for how you might do that. You could choose to put B over here on its own, but I wouldn't do that. They're going to merge together, and when I hear groups joining together, I think about one block of IP addresses. Nobody wants a bunch of little blocks of IP addresses. You have to teach all of your routers and all of your switches and all of your DNS. Everybody's got to learn about them. It's a lot easier if you can publish one. So since I don't know the timing, one thing I could do is put Group B here, but then if Group A grows past their boundary before the merger happens, they're going to have to jump over me and use 2 different networks. So that kind of backfired a little bit. So why don't I give Group B this one, because they're very confident it's never going to go past this. So I can make this Group A, and I can make this Group B, and I can make this, you know, growth, AB growth. Do something like that. And when they get together as one group, this is one route. It's a /23. Now you see why I put the 23 in there a second ago. I wanted to show you all these guys will belong to the /23. So to the rest of the company or to the rest of the world, they can advertise a /23 single route and know that all the packets are going to come to their router. And once they're at their router, then they can figure out how to split them apart, send B theirs and send A's theirs, because they'll have their own specific routes at that point. Make sense? Yeah. So what am I going to do with C? How many does C need?
4 times the 120.
Why does it need 4 times that? Yeah. Yeah, so you can do it that way for sure, right? I'm okay with that. And that's accurate, but if you didn't do it that way and you did it with a smaller number, I'm okay with that too. right? Because I don't expect you to be perfect on this stuff, right? I mean, I did give you the number after all. You could just take me at my word and just say use that many. But you do need to multiply it by 4 for point to point. So do I have enough addresses to do that?
Think about how many addresses you see each subnet that has only one router at the end.
4.
Yeah.
So it's 4 times 520.
So I need 500 out of there. So I'm basically going to use both sides of this thing. I'm going to use a /23 for that. And I'm kind of out of addresses.
Yeah.
So this won't work. I could start over with a /21, duplicate the 23s and stuff, but you want to take a picture of it because as soon as I type in 21, it's going to disappear. So if you do that with Light Mesh, the other thing you can do that's kind of cheating is just, oops, you know, yeah, exactly. Yeah, that's, I mean, who wouldn't, you know? So I don't want another tab. I want another window. Yeah. So I can come over here and do it. Now, the thing I don't like about this is it wastes tons of addresses. So let's do a /21. If it's not too much trouble. Okay. /21. And I want my 23 here. And I want a 22 to handle group C. And I'm going to put another 23 here for group D.
Wasn't group D like really small?
Yeah. So we can continue to subdivide that. So I can put my A here, and I put my B here, and I put the expansion here, and then I put group, this whole thing was just group C, right? And then this one here is group, I don't know, how many does it have, 100? Group D?
Yeah, 150.
150, so it at least needs a 24. So it's not super tiny.
Well, group D can
250? Is it going to D like David?
No, it only uses half of the people that's working, so it's 100.
Yeah, because only half of them are logged in at a given time. And it's not a point-to-point necessarily, so.
125 for the 10%.
Yeah, and then times 4. So how many do you think D needs? Yeah. Because the total was like 300 or something? So why didn't you multiply it by 4? It's a point-to-point circuit. You're going to VPN in. As soon as you VPN, you're part of a subnet. The reason why you don't have to multiply it by 4 is because you all trust each other and you're all on the same subnet. That's what a company will do, and they will isolate traffic with a switch instead, with a virtual switch. But yeah, it is a separate connection, but you're all part of the same, yeah, it's a virtually private network. Yeah. Nope, 150. The only reason you don't have to multiply it by 4 is because the company doesn't care if everybody can see everybody else's traffic. So they're not going to isolate it that way. They will still isolate it because you're probably on low bandwidth. If you're VPNing, you're probably on a phone line or something. But they'll do that with a virtual switch. They don't give everybody their own subnet. Okay, so 150 is big enough. Therefore, I'll give it, 250 when we have growth. Right, as long as you kind of understand this concept, sort of what, and you know that this tool will help you. What's far more important than the tool to me is kind of talking through how do you figure out how many addresses I need. And remembering that point-to-point networks need 4, and that a VPN is like a point-to-point network, but the company doesn't care, right? So you'll see that kind of stuff, and you'll get lots and lots of variations if you start playing with this stuff. What would be really fun to see is if you buy a commercial VPN, like the one you guys use to all steal sports games from the U.S., see what you get for that. See if you get a /30.
What?
For a VPN that you use to watch television in the U.S., you're not working for a company. You're not. When I worked at Cisco, I used to use their VPN to watch stuff in the U.S. Right? But now I have somebody else's VPN, so it'd be interesting to look to see what did they give you. Did they give you a /30? Did they give you a /25? If so, it's possible lots of people can see your traffic. And so it's,
For example,
yeah, yep. So you can always look. Okay, Yes, sir.
On the second question, which is with C, which is gold.
I did this as Group A, Group B, growth for Group B, C. C is up here. It needs a huge block. And then one of these is D. Just might as well make it the first one. That's one way to do it. So instead of having to type all that crap in, why don't I show you like this? And we'll come over here. And I think what we settled on, I think what we agreed to as a group is that this was A, this was B, this was C, and this was D. Well, this is reserved, wasted, reserved, and then this is also reserved. So if you want to tell me how many addresses you're not using, A is going to use 265, right? And how many do they have in here? They have 5. They have 256. And then I gave them another 256 here, that growth one, and they're going to use 265. B was given 256 addresses. No, they were given a, oh, that's not right. This is 128 in that second group. B was given 128. And they used how many? 100? Is that what B had? 115. Correct. Because that this is sitting next to them for them to grow. They need 265. 256 is not enough. And I didn't want to give them a whole 512, so I gave them a 256 plus a 128.
We want to see simplified for because you say precisely here that.
Yeah, but don't worry about it. Yeah, but don't sweat it. You can do what you're saying. You can use their numbers, but I don't care. All right, so you're not going to change the network design based on 1 or 2 numbers. If you're that close, you need to give them more anyway. But I'm totally okay with that. What he's pointing out is these numbers here, they've already subtracted off the network number and the broadcast address. Okay, so B wasted 128 addresses minus the 115 it used. A wasted the 256 plus 128 minus the 265 they promised they're going to use. C needs how many? I gave them 512. No, I gave them more than that. I gave them 1,024, right? Hmm? How many was it? Okay. So, is that? Yep, that looks like a lot. But we got forced into that. And then D, I probably could break this up and make this reserved over here if I wanted to. But D has 256 minus 250 times 1.1 squared, because it grows 10% for the next 2 years. And you add all that up, and that's how many addresses you've not allocated. Okay? Just for the record, that seems too hard for an exam. I probably would not put that on a test because it takes too long. And you can get tied up in knots. If you don't have confidence, you'll spend 20 minutes on it. So you got questions about it, ask them now, or forever hold your peace. Okay, we've already talked about this. What's the relationship between the size of the fragment offset and the fact that it must be 8 bytes? Because you stole 3 bits from me, and so I pad all of my 13-bit numbers with 3 zeros at the end. And everything is a multiple of 8 that way. Because I still needed to represent just as big a number, and you only gave me 13 bits. So to represent a number that's just as big, which is 2 to the 16th, I had to add 3 bits back in. And those are all going to be zeros, obviously, because there's no place to say what they are. If you had a place to say what they were, you'd have 16 bits. But you don't. You only have 13 bits. Okay, following fragments are observed in Wireshark. Which of the following characterize this fragment? So it's got the more fragment bit set. Okay, so how do we tell the answer to this question? So let's look for the offset. Do we see that in here? Where's my offset? I'm going to scroll through. Here we go, right here, 13 bits. 4, 8, 12, 13. There they are. They're all zeros. So the offset is 0. So this fragment starts at the beginning of this datagram. So it's the first one. So that part, I'm comfortable with that. Because the offset is 0. So here's what happens when you have a fragment. You discover that a packet needs to be fragmented, okay? And I got to move this tool over because I need to see this. Okay, here we go. So I decide the thing, why isn't it doing that? Here we go. I decide that this packet needs to be fragmented. So I'm going to break it into several smaller packets. The MTU for my network tells me how big each one of them needs to be. So there's a header that was at the front of this over here, and that header is going to have to get copied into each one of the fragments. So I'm going to ignore the header for just a minute. And let's say the size of my packet that this network will take requires that I break this thing into 3 packets. The first 2 are the same size, and the last one, so close. The last one is a little bit smaller. All right, so I'm going to build my 3 fragments here, and I'm going to let them loose on the network. Each one of them is going to have a header that I've copied down, and I'm going to turn them loose on the network. There's no guarantee they arrive in order. There's also no guarantee they don't get further fragmented even more. Maybe one of them takes a route, but it has to get fragmented. So these things are going to show up in pieces. How do I know how to put them back together? I need the offset to help me. So the very first one, when I get one that has an offset of 0, I know it's first. All right, so let me turn this off. So if the first one that arrives is 0, then I make a space for it here. It's 0, and I know how long it is, and that's all I know. I know there's more fragments. I know I'm not done. I know I'm not done because there's something that says there's still more. But wait, there's more. Right? So I'm not going to send this to the application yet. If this more bit had been 0, then I would know this is also the last one, and I could send it up to the application. All right, so now I wait. You don't. You have no idea how long it is. Great question. You do not know how long this is. So another one comes in, and it starts at byte 800, better known as segment offset 100. So you scooch over and you make some space. Now you know that your datagram is at least 800 plus the length of this one particular packet. And then another one comes in that's 400, and you're like, geez, this thing is like a monster. And you figure it up, and then you get one in here. Let's say this was 100 bytes long. So you get one in here that's byte number starts off at 100, which is never going to happen because it's not a multiple of 8. Yes, it is. 15. So this one will have an offset of 15, and let's say it's really, really short. And then you get one that's an offset of 20, and it's a little bigger. You just keep filling the holes until you have a contiguous block that starts with offset 0 and ends with a packet that has no more fragments after it. It has this bit set to 0. Only then do you know you're done. So once you get all the pieces back together, if the timer hasn't gone off because you're impatient, then you can put them all together and send it up to the application. And what will you have sent to the application when you've done that? You will have sent to the application this original red datagram that the upper layer gave you earlier. So TCP is very happy. It handed you something, and that's exactly what you handed TCP at the other end. And that's the idea. So this one is the first packet because it has an offset of 0. It's not the last one because it has more fragments set. It's not the middle one because it's the first one. It's not the last one because this is set to 1. So every datagram you send is a fragment, even the ones that aren't fragments. The only thing that makes a regular datagram any different is the offset is 0 and more fragments is 0. Most of the packets you send, that's what they look like. It's the one and only one, exactly right. Most datagrams are just solitary datagrams. Good, yeah, you got it. All right, make sense? Okay, what else did I ask you in this one?
the original diagram was 15,008. And for the next the output of the next fragment.
Okay, so assume this is not the last fragment. Yeah, it's one of several fragments. That's also true. Those are the only two I think that are correct. All right, assume it's not the last one and one will follow. If it is also not the last fragment, what will its offset and total length be of that packet? So I don't know that I wrote this that it made, I don't even know what I'm asking. So how would you guys know? Am I asking like the one after next, or if am I asking for the next?
I thought it was the next.
Okay. So what is its offset going to be? How will you figure out what the offset will be?
The length minus.
You take the starting offset of 0, you add to it the length, 1500. So 0 to 1499, except you take away 20 for the header, because it tells us the header is 20 bytes, which means there's only 1480 bytes of data in here. And so divide that number by 8. Yeah, that sounds right. All right, so let's make sure we're not losing anybody here. Right? So you don't know, you know how long the fragment is, you don't know how long the original datagram is. That's what you don't know. You have no idea how long this is going to keep going until you get the fragment with the 0 in more fragments. And then you know, then you can calculate how long it is. So we know that the total length of this is 1500 bytes. We also know the header was 20. So data is 1480. All right? So I started at offset of 0. Started at 0. I multiply that by 8 to get the first byte number. I add to it the number of bytes that I can fit in this datagram. I get the final byte number. The last one is, this is going to go from 0 to 1479. The next packet will start with 1480. And to figure out the offset, I have to divide it by 8. That gives me 185. That 185 goes into these 13 bits here. You figure out what it is in binary, and you write it down here. Yeah, you can. Exactly. Because this fragment, I'm trying to figure out what the offset is for the next one, right? So I got to figure out what this one is first. And it's not always going to be 0. So I wrote this like you would write your code. You just take whatever the current value is. Doesn't matter if it's 0 or not. You're not going to do a special case for that. Just multiply it by 8 and do that. All right? Make sense? All right. Because that's what we do for offsets. Multiple of 8. Exactly. Exactly. Yep. And the length will be 1500 because the length includes the header, right? Just like it did up here. You just copy. And you can be confident that if you have an infinite stream of data, all the fragments will be the same size when they leave whatever point you're at until the last one. The length will be the same in every one of them. You're not going to adjust sizes as you go along. You want to get this over with. Send as few packets as short a distance as possible. So you put as much data as you can into each one.
So if the first one was 1500,
Yep.
Oh, and yeah, that is the last one. But it says in the question that it is not the last fragment.
Correct.
So that's why.
Exactly. I told you it was not the last one. Ah, thought of that. That one actually thought of. Okay. Yeah. Yeah. What will the values be for the last packet if the original IP datagram had 15,008 bytes of payload?
Can I send a packet of telnet?
Absolutely. You can send packets of 1 bytes, and you do all the time for telnet.
Yeah, like goes from 15,000 to 15,008. Yeah.
Basically, so let's work through it. So I have 15,008 packets. How many can I put in a packet? Exactly, 1480. How many is that? It's 10
Yeah,
plus something. Duh. Of course it's 10. Geez, Louise, I can't do that in my head. Really? It's gotten to that? I can't like add a zero and good God, like I need a vacation or something, I guess. So that'll take care of 14,800 of them. And how many is it going to leave you with at the end? 18, 9, 9. So it's going to leave you with 208. So you're going to fit that. Is that a multiple of 8, I hope? Yes. So it's 42. It is 26. Why would I do need a vacations. So divided by 8 equals, tell me again? So I'm going to have 26 bytes in my last one. So I need 10 packets of length 1,500 apiece, but they're only going to carry 1,480 bytes of payload plus 20 bytes of header. And my offset only cares about how far away am I through the data. The offset doesn't care about how far away through the header I am. So I get to the very last one, and I've made it up to byte 14,800. That's where the last packet will start. It will go from 14,800 up to 15,008. Correct? So the last packet starts with, so what is this number divided by 8? 200 and what?
1,850.
1,850, that's the offset. Make sense? And the length of this will be 208. So we really don't ever need this, do we? We'd need it if there was one more past the last one. We want to know where this packet starts, not where it ends.
1,480 is because the total length is 1,500 minus 20, right?
Correct. Yep, that's what I tried to point out.
Oh.
That's okay. No, I'm not saying don't ask because it's there. I'm just saying I tried to scribble it there. All right, makes sense? So I can fit 1480 in each one. The last one's going to start with 14,800. See, so it wasn't so torturous after all. Just, yeah. Well, me too. I mean, you got me doing it here, right? I mean, I was perfectly willing. I didn't know that was wrong until I thought about it for a second. So these are not trivial, but it's not hard to write the code. It's hard to write the code and debug it and have confidence it's right, but it's not that tough. Once again, we see that something that is so important to the world is not that complicated. Right? It's kind of surprising. All right. Do you guys know the answers to error control and flow management?
We thought that the error control
Oh, I did? How convenient. Would a router recombine fragments into a whole datagram? Be careful. The answer is never. Yes. The answer is yeah, so a router that's routing will never reassemble fragments. But if it's the destination, it will. A router can be the destination. Like when you telnet to the router, or you open a web page on the router's web server, or you download new routing software to the router, then it's the destination. Make sense? So super tricky. For a minute, they'll probably shut you down. Tech will shut you down if you try that. Yeah. Oh, good. Yeah. So you want to be more clever. You want to generate random numbers and start poking. You don't want to get caught going blah, 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 because they'll just go
Yeah.
giant fly swatter will come and, okay, flow control and air control. One way to check whether they have these things is to go look at what's in the header. So here I see a receiver window in the TCP header. That tells me TCP cares about not overrunning the other end. He wants to know how much space you have left. Do I see anything like that in IP? ID number, fragment offset, time to live, the protocol number, the checksum, that's error control. Checksum's error control. Yep. Flow control is making sure you don't overrun the far end. The reason why the offset will work is only because TCP is doing windowing. Yeah, the layer above.
It doesn't have full flow control?
It does not. IP has no flow control. And do you see anything in here that has a space for the router to set, like the explicit congestion bit or, yeah, I don't see anything in here either like that. I think we know what all these fields are, and none of them are that. Now, we haven't talked about all of these in here exactly, but that's okay. So I would, in the absence of proof to the contrary, I would say no to both of these. Because I don't see anything in here that they would use to do that. And I'm trying to get you to look at the header. Okay, ICMP, do you guys know how to do this one? Do we need to go over this? We might. So this is directly out of the book. It's straight out of the book. And the book is in a PDF form on the class drive. You can, don't act like you didn't know that. All right.
No, I didn't know that. I know the book was
there we go. That's better. Nice recovery. You're welcome. All right. Okay, where the heck is it? Is it in here? No, the students the other day told me it was here.
Maybe you can think you're trolling.
No, maybe it isn't, and they're trolling me because I specifically asked them. I go, really? It's there? They go, yeah, it's there. I'm like, okay, I don't see it. Do you see it? Stupid WebEx. Well, I'm going to...
I already knew that it was
So you were not fighting it out?
yeah, that's why I...
Yeah. Okay. That's why you were kind of quiet when it's like, oh, let's let him think it's there, fine, whatever, crazy, put okay. All right, let's go and get it.
Well, I didn't really say anything.
You have options. Either words.
Silence is louder than words. Do you guys have that phrase in Spanish? Yeah. Okay, so here it is. I can put it in extras. Now you can read all about it. It's not, okay, now it's synced. Okay, so if I go ICMP,
Like 1,028 pages.
no, I just searched for ICMP. Are you kidding? Chapter 9 it says, so let's scroll down.
Then what you're saying is that it's painful that it's 1,029 pages,
Yeah.
not 1,028.
Oh, gotcha, yeah. Well, you'd have to pad this. I'm sure they did pad it with paper. Why did I say that? No, seriously, why am I positive they padded it to a number 8, to a multiple of 8? Have you ever looked at how a book is built? They take 4 sheets of 5-fold paper, make a booklet out of it, and stitch it in 8 pages at a time. Sometimes it'll be 16 pages at a time. But if you look at the bind of the book, you can see the little mini books that they've glued together. So it is always going to be a multiple of 8 or 16. Always, 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 always. So that's why when they fold the paper together, the edges don't line up. So the last thing you have to do when you do a book, you have to cut it off. And older books don't. The pages are different lengths. See, you learn about all kinds of things in here, right? I had to write software to interfold documents into booklet form. That was a huge pain in the butt. Okay, so here's ICMP. That's the package. I want to go in here and look at the little table. There it was. I went right past it. Okay. What is it going to show me? Error reporting messages. Okay, here you go, right here. They are either error reporting or query. Right here in the book. Those are your two options. Those are the two types of ICMP packets, error reporting and query. Yeah, but those are examples of specific types, codes. But the two classes are error reporting and query. Up here. A destination unreachable message is type 3. So we can scroll through here and find it. Here it is right here. Destination unreachable is type 3. And the question is, it has 16 codes defined. Which code numbers are for messages that can only be sent by a host? The protocol is unreachable. TCP is not running. OSPF is not running. That sounds like something inside of a host. Routers don't run UDP and TCP. And then the port is unreachable. Same thing. If you scroll down a little bit, it'll actually tell you only codes 2 and 3 can be issued by a host. If you read down a little further, 2 and 3 can be created by a host. Yeah, yeah, it literally says it. I told you it comes right out of the book. Destination unreachable message, blah blah blah. Which pair of ICMP message types and codes are caused by running a successful trace route? So let's search for trace route. Here it is. Debugging tools, ping and trace route. We'll skip past ping and get to trace route. So what does it do? It's going to walk us through it. It sends a package with a TTL of 1. It receives it and complains back with type 11 code 0. And finally gets to the end and responds back with code 3. Type 11 code 3. Oh, it is type 3. You're right. Type 3 code 3. Sorry. Yep. They're both type 3. So it's right out of the book. I think that's right. So an unsuccessful trace route would be one where the host at the end said, as a matter of fact, I do have something running on that port. And you're like, because you wanted to reject it. So a successful trace route is one where it doesn't, and it gives you an error. Exactly. The successful trace route causes problems. Okay, we find 2 IP headers. We know it's an ICMP packet. Which ICMP-related task would be normal to find 2 headers? Well, one of them is going to send back an error, and the other one is just a query. Only errors chop off the head of the offending packet and mail it back to you. The queries don't. Like, ping is a query. Trace route causes problems. So you don't ask for the error message back. It will send you the error message back unannounced. Ping, you have to say, would you please tell me, would you please respond to me? So it's a query. And those aren't errors. All the other ones are. Okay, ARP. You find an ARP packet on the network that has the same value for sender and target protocol addresses. Do you ever remember seeing one of these? You saw it in the lab. Do you remember what it's called? There's a different name for the one I'm thinking of, so let me see if I can find it. I don't remember it called that, so let's see. Whoops. Hold on, let me find it. Sheraton. I grabbed a big Sheraton one here from downtown Monterey. I capture them all the time on airplanes to see if there's any like flight logistics data flying around and stuff. And it occurs to me I'm probably not supposed to do that. Yeah. I'm glad I wasn't on a 7, whatever it was, max. Of course, there's a lot of reasons why I'm glad I wasn't on that. Of course, I wouldn't be here to tell you that story. So here's a bunch of ARPs. The typical ARP has a different target address than a source address, right? So I'm just going to scroll through these packets, and I want you to tell me if you see one where they're the same, okay? So I'm going to go down. I don't see one up above. That one. They're the same. Why does this ARP exist? It's advertising itself. It's a gratuitous ARP. You'll do this whenever you want people to know you're there. You'll also do this whenever you change your IP address or your hardware address to let everybody know. Or you'll just do it periodically. So to force everybody's ARP tables to update, or to force all the switches to update. If you move to a different port, your code is probably going to send a gratuitous ARP because it sees your network went down and back up again. You could test it on an older system like a Mac here. I could run Wireshark and unplug the Ethernet cable and plug it back in and see if a gratuitous ARP appears. And you can do something like that, for example. Okay, so that's a special type of ARP. In an ARP request, the value of the target hardware address is all zeros. That's inside the ARP packet. What is the value of the hardware address in the frame? Well, let's go find one. Here's one that's all zeros. In fact, all these are all zeros. If I go down a layer, what the hell is it doing? Stop. I open up Ethernet. What is the destination? This one's actually kind of weird. These aren't this is an ARP storm, so it's not totally legitimate. So this is not exactly what I want because I've learned others. Let me open a different ARP one. This is I caught bugs going on here. ARP PCAP. Let me find a normal one. This one might be normal. Yeah, these are normal ARPs. So he's looking for an address. So the ARP target address is all zeros. What is the Ethernet target address? Yeah, it's a broadcast. It's all F. That makes sense. It needs to go to everyone. If you knew who it needed to go to already, you wouldn't need ARP. You know, and what we were seeing in the other one is they were sending it to the router because they already knew his MAC address. They're asking him, will you please help me find this? So it's acting as a proxy because what they don't want in the hotel is for me to send a broadcast to all the other hotel people, to all the other rooms. So they force my ARPs to be proxied through the router, and it sends me a message telling me I'm your proxy, so I just send everything to a specific hardware address. And it usually knows the answer, so it doesn't even have to send an ARP. It will just respond back itself. Okay, here's a trace route. So the only thing I want you to get out of this, guys, is this is not like you've seen in all the other books that you've looked at. And they've sort of changed things around on you, which irritated me, so that's why I gave you this problem. They always tell you that these protocols are 4 bytes wide, right? Everything's 4 bytes wide. But if you're doing an actual ARP datagram, an ARP packet for this guy here, the hardware address that we're using for this technology is 48 bits. It's 6 bytes wide. It will not fit in a row that is only 4 bytes wide. So the way this ARP packet, and only for these technologies, you change technologies, you change the logical or the hardware, the ARP packet will restructure. But for this particular one, you're going to put your sender's hardware address here and here. It'll straddle 2 rows. And then your protocol address is going to start here and end here. And then the next hardware address will straddle 2 rows. Finally, you're aligned back again by the end. So I want you to tell me what these are. So what is the sender hardware address in this packet? All right, so 00, Give me just the first 4 bytes. 0023 DF A3. Where do the last 2 bytes go? Next row, right? Just continue on. And then what's the sender's IP address? Do we see it here? Let me scroll over so we can see it on the screen too. Oh, it's right there. It's right underneath it. 192.168. That's the first 2 bytes. What are the last 2? 1.248, right? No, that's fine. I don't care. Target hardware address. You can scroll over and do this. But what did I ask you in this question? If the discovery of data required to accomplish this feat of putting the frame on the network was thanks to ARP, complete the table with what the ARP request would have looked like. The ARP request, not the reply. So in the request, do I know the hardware target yet? That's what I'm requesting. So it's going to be all zeros, right? Sorry. Glad you didn't hire a scribe to a monk or something to write this on parchment or something. And then the target protocol address, that we do know. Yeah, you bet you would. You do reply if it's a reply. So this is a request, and the protocol length is 4 bytes. The hardware length is 6 bytes. You can put this as a hex number, decimal, whatever you want. Hardware type is Ethernet. I don't care if you put the number in there. Protocol type is IP. There are numbers for that. That's not why I'm giving you this exercise. I'm giving this exercise for this down here. So, did you guys hear the question he asked? It tricks lots of people. So if it's a reply to this, then the sender and the target are now reversed. So you'll switch those 2 roles. Blue goes to the bottom, purple goes to the top, green goes down, yellow goes up. If it's a reply. Yeah, if it's a reply. You will reverse them. Or you won't get the reply. Or it'll fail as an ARP because you won't get a reply. By the way, I don't like that. I'd rather do it the way whoever you're pointing at, because it still says sender. Well, the original sender is still the same original sender. So there's debate over whether you should have reversed those, and it confuses people often. Okay, I'm sorry. I interrupted you. I don't care. No. I don't care what you put there. Okay? That's not why I gave you this problem. I gave you the problem so you could see how this wraps around. We really do try to stick to the 4 bytes per row if we can. Okay. Have we killed it? Is that it? All right. That took about twice as long as the other sections. So I'm a little nervous if we're going to finish the other one. So if it's okay with you guys, can we just dive right in, please? Okay, because I don't want to run out of time. So the longest matching prefix is this concept that says you look through the routing table for something that has the network number that you're looking for, or as much of it as you can get. That's the idea. So the first part of this is super, super easy. If a packet arrives with 1010.0110, which route will you match it to? Well, this matches the first part. This matches the first 4, but the 5th bit is not a match. And the 6th bit is not a match here. So the only one that's really a match is this one. Therefore, if a packet arrives with this destination address, you will look in your routing table, you will see this, you will send it out port 4 to this router address. That's your next hop. Do you see why? What I try to do is take my destination address and I try to match it with all of the rows in my routing table. And there's a few that start off right with 1010. Yeah. The problem with this one is the 5th bit does not match my 5th bit. Therefore, this cannot be talking about the same network, and therefore I should not route my packet down this port thinking it's going to get to my network, because I have no reason to believe that. All right, make sense? Okay, next one. 0010.0110. Which route matches that? None of them. There's no 0, 0 in here. So where are you going to send this packet? To the very last row. Port 9 and to that router. All right. The next one is 1010 0010. Here's a 1010. Here's a 1010. Here's a 1010. This one's out because it's the wrong 5th bit, but this one matches perfectly and this one matches perfectly. How do I know which one to pick? Number 4, because it's a longer matching one. All right, so it's the longest matching prefix. This turns out to be something that got covered in last year's book. It's not at all covered by this year's book, but just remember the longest matching prefix and you'll be okay. Salud.
But what if we don't know the address?
Why don't you know the address? What is this? So what this means is there's no next hop. So it's attached locally, the LAN. I can see this address on a LAN. So I can ARP out for exactly this IP address I'm trying to reach for this guy, and somebody will respond from that local network. There is no next hop. I am the last hop. It's at some point every packet needs to be directly delivered. All right, makes sense? Okay. You can draw binary trees to try to do this. Nothing. For the next hop, there isn't one. There is no next hop. It's blank. You're at the end of the road. No more hopping. Calm down, little bunny. No more hopping for you. All right. It's one of my favorite Spanish words. Sounds nothing like the English word. Yeah, rabbit, congrejo. Okay. What we need to do is try to draw a tree. I just want to give you an idea of what a data structure looks like that you have to build inside a router and how it is very sparsely populated, which is a surprise. So let's suppose I start to build one just for this. So I have a route in my routing table that is just a 0. So I chose to go to the right for 0 and go to the left for 1s. So I'm going to draw the 0 to the right, and I have a node there. I have also a node here at 1. My next network is 1, 1. And I have a network that I want to define there as well. The next one is 1, 0. So that's going to look like this. Oops, I thought I clicked on it. I'm going to have a 1, 0. And you can see where this is going, right? 1, 0, 1, 1, 0, 0. So it's not a balanced table. This one happens to be unusual because every node has a terminal network associated with it. Let's try to do the one up here. And on the homework that you're doing, if you do the first couple and you say, I understand, you'll get the points. You do not need to draw the whole table. I want you to master the concepts, not all the detail in my particular diagram. I don't care about my diagram. And so I've got one that's a 1, 1. Is it okay to make the ones go to the left again? You guys okay with that? All right, so there's a network defined there. Then I have a 1, 0, 1, 0. So that's a 1, 0, 1, 0. And so there's a network here. Then I have a 0, 1, 1, 0, 0. So I have a 0, 1, 1, 0, 0. So I can't make all these exactly the same size, or they're going to run into each other. But that's okay. If you, like me, carry more than 3 colors of pen in your backpack with you right now, you are the type that will go back and draw this perfectly symmetrically. And you know who you are. All right, so, yeah. So do I need to go through the rest of this, or you guys see what's going on? One by one, route by route. The next one would be 10101. So I have most of it here, 1010, and I need one more here. So it's not just the leaves at the end that you're referencing, but you can see this one's more sparsely populated. It's a directed acyclic graph, basically. So you can use this to do pattern matching in the ternary content addressable memory to figure out if does anyone have a route for this. If you don't have a route for this node, then prune the tree. Do you have one for this? You know, if somebody's asking for something out here and you don't have it, start pruning it off logically. Once you get to here, use this route instead. That'll be your longest matching prefix. Make sense? Okay. So I just want to touch on that because that's beyond this class even. You don't. Nope. The default is just going to be sent out a port because you have no match. It's nowhere on your tree. All right. If you will give me, I don't know, 5 to 10 minutes of concentration, you'll kill this one. You guys may go faster. I have a funny feeling you will. First of all, let's just get a couple of things out of the way. There's a LAN that's connecting the routers. There are 3 routers on here. That's what those hexagons are. Do you see the LAN that's connecting the 3 routers together? So help me draw it. What is the network number for, or what are the IPs for that LAN that is connecting my routers together? 125s. All right, great. So I need to grab the port off of each router, right? But only the port that belongs to that LAN. All right, so far so good? So everything we're going to do, if we have to go from one router to the other, we're going to go across this LAN. Agreed? The thing on the bottom is who knows what, some sort of maybe radius controller for passwords or a NAT device or something like that. It looks like a PC more than a switch to me, but it has an IP address, so it's on the LAN. Yeah, yeah. All right, we ready to start? I've given you the tables for the left router and the right router. We're going to ignore those. You can come back to them later to practice more if you want. Our task is to fill in the middle, the middle router's table. So the first thing he tells you is there is a subnet on this network somewhere, 1220/29. Where is it? Why?
I don't know. It says port 2, IP.
Well, let's go through it. So it got, because it got partly done, and I didn't override it again. So we did that in the first one, and I partly override. So why is it 2? Why is it port 2? Why isn't it port 1? I see 122s here too. How do I know it's this one and not this one? The answer lies in the subnet mask. Yeah. So where is the 29th bit? In the first, second, third, or fourth number of an IP address? All right, you guys agree? The 29th bit. So 1.2.2. And I'm going to write it out in binary since it occurs in the last one. 0, 0, 0, 0, 0, 0, 0, 0. So if I do a /29, where is the 29th bit? The 5th bit is the 29th bit. So these 3, I'm going to put them in a different color then. All right? 0, 0, 0. So what this means is if it's a /29, all of the first 29 bits must always be the same on all the addresses on this subnet. And I can only play with the last 3. So let's test it out. What is 1 in binary? Well, 0, 0, 0, 0, 0, 0, 0, 1. All right? No problem. What is 2? That. What is 8? 1, 0, 0, 0. This requires I change a bit that I am not allowed to change. So that subnet cannot be over here. It must be over here on port 2. And there's no next hop. So port 2 and no next hop, right? Okay, what about 121? Where do you see the network that starts with, the LAN that starts with 121 and has 0? That's the next over here, 1210/24. It's to the right. It's down here off the right-hand router. Do I care about whether it's this one or stuff like that? Why not? It's the next guy's router. It's not my problem because it's his problem. All I need to know is that all the 121s sit behind him, so just get it to him. And because I see a 24, that also helps me have confidence that it's all going to be over here. So I'm going to leave my router via port 3, and my destination has to be an IP address on this blue LAN. Those are the only choices. So it's got to be this one. Make sense? All right, the next one is 125. That's us. So the port, yeah, because you're leaving your router out of port number 3. To get it on the LAN and headed in the direction of where it needs to go, you must send it out of port 3 on your router. So it's going to be port, drop your style. Port 3. Got it? Yeah. And no, next hop is actually 1251. Make sense? Okay, 125, that's us, right? Yeah. And I leave port 3, no next hop. Agreed? If I want to get to 123, it's down below, so I already know I'm going to leave port 3. That part I already know. It's my only way out. And where am I going to send the next address? 1230/24. I'm going to send it to that router. And then what about 1228? Well, I really don't care about that much more detail. It's going to leave, no, this one is back up in the top left, right? This is the one that before we said couldn't be that one because it changes this to an 8. So now we know it's that one. So I leave my router out of which port number? Port 1, and what's the next hop? There isn't one.
Okay, so it started over there, then went one to the right.
Yep.
And then we left, and went to the right, like it reached the CPU at 1.212.
It reached it up here by leaving the router out of port number 2.
Yeah, and then it reached it, and it got into the right router.
It's just the port. Oh, how you got over here? The only physical connection I see is this wire and this wire, right?
Okay, I'm trying to like make the right thing. Yeah, and then it got into the PC at 1.212.
Yes. That's a direct delivery. So all you do is drop it on the LAN. There could be 50 other devices or 5 other devices or 3 other devices or whatever. But all you have to do is drop it on the LAN and the device will see it.
Then we have 3 more lines.
With different network numbers. So this table basically says if you receive a packet with a destination address and you determine that it matches most closely this prefix, where should you send it?
But I don't know, like the last 2.
The last 2 entries? All right. So the last 2 entries, where are all of the 1, 2, 3s? Yeah, so you need to get it to this router. What address on this router can you see? It has 3 IP addresses. Which is the only one you can see? Why is that the one that you can see? It's on your LAN. And you belong to the same subnet as he does. You are also a 125. You can only see devices on your LAN. If you have to route to get to the router, it's not your next hop. Somebody else is your next hop. You have to be able to get directly to him in order for him to be an eligible next hop. So how am I going to leave my route over? Which physical port? Do I leave over here? There's no connection to these down there. Do I leave over here? Again, there's no connection. The only one that goes in that correct direction is the one that leaves this port number here and goes to this IP address. Does that make sense? Do you understand that line now? Okay. So I can see it right here. So if I need to reach that address, something on that network, then I'm obviously going to send it to the side that where that IP address itself exists. But this is not telling you how to get to an IP address. This is telling you how to get to that network. And it happens to start with 1228. But this is an example where I went ahead and assigned the network number to an actual device. Because you can. It's okay to do that. You don't have to reserve the network number. There is no next hop. This is the table for this router.
Well, no, yeah, but like,
So all I got to do is send it out the LAN, out port 1, and presto, it's on this LAN. Got it? If you need more practice, try looking at the other two tables that are in here. Okay. How many addresses are in the bottom left-hand subnet? Do we know? Let's go hunting around. 1, 2, 3, 2. I have a 1, 2, 3. It's a /24 here, so that doesn't really help me. What about on the left router? 1, 2, 3, 8 /29. There it is right there. 1, 2, 3, 0. This one's the 1, 2, 3, 0. This one's the 1, 2, 3, 8. So this is the 1, 2, 3, 0 /29. So how many addresses are in a /29? 32 minus 29. 2 to the power of that equals 8. Your addresses are 0, 1, 2, 3, 4, 5, 6, 7. Which one do you have to reserve?
7.
The broadcast address. And which ones have you already assigned? A 1 and a 2. I don't care if you reserve this one or not, but just to make peace with the world, let's reserve it. So what does that leave you with?
4 left.
4 left. 3, 4, 5, and 6. So did I go down too far? Yes, I did. It's going to be 3, 4, 5, and 6. Now, I bet that's typoed still on yours. It doesn't look like this, does it? Do I have like 6 in there twice? Okay, because that was typoed badly earlier in the week. Make sense?
Yeah.
All right, let's get the heck out of that problem and get to the next one. Sorry? How many addresses are in the subnet assigned to the LAN? 1, 2, 3, 2. We said it's got a total of 8. It's a /29. All you got to do is go look for that in the other routing tables. Somebody will know. Yes? Usually, but you don't have to, but you will not be routing between the two. If you leave them on separate ports, you will have to turn routing off because they are in the same subnet. You will turn on bridging instead. So you can have them physically separated. Electrically, there may be some reason you want to do it. Some of them are on 100 base T, and that's the only cards they have because they're old. And the other ones are on 1 gig E, and you just have a gig E switch and 100 base T, so they can't physically be. So you'll plug them into separate router ports, but you just bridge them together. There's no routing entry between the two. I mean, what would the routing entry say? It's the same subnet on both sides, right? So you just turn routing off, and you basically turn those ports into a switch on your router. That's done all the time. Right? Make sense? Okay. All right, last one. This is one of the crappy diagrams where it's not drawn very accurately. It also has a bug, an error. So the first thing I want to do is draw that for you. This should be 128. The address of the router port connected to M2. Correct. That's wrong. Okay. A packet arrives at our one and only router with the address of 145.14.192.71. What do I do with it? So here's an entry that starts with 192, but I don't see a subnet mask here. So how do I know that the 71st address after this also belongs to this row? I go looking around. I find 192 here, and it tells me it's a /18. So what is 2 to the 32 minus 18? It's like, I think it's like 4,096, something like that, but it's a lot bigger. Yeah, because it's a /18. 16, well, okay, it's a lot bigger, but it's a way bigger than 71. So I know that this gray subnet for sure at least has this address in it. So you send it down port M3 because that's the one that connects to the gray box that has the 192s in it. Okay, what about the next one? 115 .14.128.22. Correct. There's no block at all for this one. So where do I send it? To the default route, somewhere out on the internet. I would say M4, because there's a port for that. It goes out. And there isn't one. There isn't one. There's only one router on this diagram. So you're the last hop. We don't know the IP address of this one. If I drew this diagram, I would have given it to you.
What could be there for some other item?
Drop it as invalid, or discard it because it's a private address and it shouldn't be forwarded. You know, things like that. Yep. Yep. Exactly. Well, there is, but they didn't tell us what it was.
So we can standard that.
So you can say XYZT if you want, I guess. I don't know what this is here for. I mean, it doesn't cost any more ink to put a number there. But maybe you just didn't want to confuse people with too many numbers. I wouldn't, no, there's no other action. All right, how many addresses are available in each of our 4 gray box lands? You just told me the answer to that. And why is it that number? Because it's 2 to the 32 minus 18, which is 14. 2 to the 14. And how do I know it's 18? Because it says so right here. They're all 18s. Okay. The overall block is a 16. Have you assigned all the available addresses in these boxes? Well, so the question is, between a 16 network number and an 18 subnet mask, there's 4 groups. And there are 4 groups on this diagram. Therefore, you've assigned all 4 groups. So the answer is yes. They're all allocated. If it was like 15 to 18, that's 3 bits. There'd be 8 groups. And then if I saw that you only had done 4, then I would have said, no, you haven't allocated all of them. All right, so that actually answers the next question as well. If you make this a 15, you actually have 8 of these 18 lands. You move back one, so you've doubled the number. So you'd be able to do 4 more of these, 4 more 18s. That makes sense? Another way to check that is you had a 16 to 18. 18 minus 16 is 2. 2 squared is 4. Now you've got 15 to 18. And so it's 2 to the 3rd. You have 8. And you don't have to subtract off a broadcast, or just don't worry about any of that stuff, okay? You can do it if you want, but don't do it if it's confusing to you. So you'd have 4 more. All right, so the exam will come from these problems. I will give you a study guide. You can bring a cheat sheet. I will give you both solutions to both of these problems today because we've gone over all of them. So what's the point? Right, so turn in what you can. If you get one of these and you go, I get it, then I'll go, great. Saves me the trouble of grading it, and you told me you've mastered the concept. We'll find out on the test. But, you know, I don't expect you to waste a bunch of time drawing a tree with 20 branches. If you can draw it with 4, I'm happy. Yeah. There you go. I understand. Yeah. I actually turned in a homework once. The year the Macintosh came out, I was the first person in line to buy a Mac. Have I told you this story? All the engineers, including Steve Jobs and Wozniak, they all signed the inside of the case. And so this thing is like priceless, right? So there was a recall at some point for a power supply, and I took it to my trusted guy, and he goes, they also replaced the cover. It replaced, and he threw it in the trash, and it was already gone. They picked it up. And so it took me, I needed therapy. It took me totally to let that go, just let it go, right? That was super tough. I was super pissed about it, and he knew it. And I go, did you bother looking inside? And he goes, yeah. It's like all these names scribbled in there. I'm like, you idiot. Well, you know, my other choice was to go garbage dumpster diving, and I wasn't willing to go do that. So, yeah, that's fine. If you feel like you know what's going on, then you're good. I got number 1. Yeah, I was number 1 in line. Stayed up all night and did it. Yeah. Yeah.
Is that still alive?
Probably. I still have it. I still have the box and all the manuals and everything else. Well, the point I was telling you, though, is I immediately started using the Macintosh program called Write to do my computer science homework. And I couldn't do one of the proofs, but it looked so good because it was actually typeset, and it printed out. It was the first computer that would actually do integrals and all that. And I drew a little cloud and said, "A miracle occurs here," and the grad student gave me credit for it that was grading it. I couldn't believe it. And it totally ticked off my girlfriend at the time. And she goes, "That is so unfair. You got more points on yours than I got on mine. It was exactly the same answer." And I go, "Yeah, mine looked better. Deal with it." So you know what she did? She bought a Mac. So, yeah, you got to be, yeah, she dealt with it. All right, you can bring your cheat sheet. You can bring the study guide. I got to crank one out for you guys, but the homeworks are basically it. We're not going to do a light mesh one, I don't think. I tried last year to do one, and I gave up on it. I think this year I'm going to give up on doing it on the test, too. I think it just takes too long. There's really nothing quick we can do with it. All right, we good?
Yep.
All right. I got you out a little early. Actually, not bad. I think this is kind of the time I let the other one go. Made me nervous with the first homework, though. Stuff at the rate you want to learn?
Yeah.
Okay. It's
There
a
are
lot.
some things that I feel like there are like
That we're going really
some
fast?
solutions that feel incredibly creative, but when I see them and I think that I should not find that by myself, I'm like, wow.
No, it's an endless learning exercise on networks.
Yeah.
If you ever watch people trying to diagnose what's going on a network, they don't all go in and go, "Okay, it's obvious, everybody gets it." They argue about it.
Okay.
Always. It's always hard. It's always debatable. There's always multiple ways. That's why I try to instill this idea that there's just not my answer. There's never just my answer. There's always other ways of looking at it. I heard that there's a security problem on campus this week, and they're shutting down lots of ports.